Okay, so who we are and what are we doing? Where are we in the? If this will not work, I will just blend it. So it is computational chemistry. Our goal is to predict properties of chemicals and materials and molecules. We all believe in Schrödinger equation, and we realized that molecules have so many independent degrees of freedom, electrons and nuclear positions, that this Schrödinger equation is not solvable. So our goal, not only our, but anyone who goes into the direction of computational chemistry, is to reduce, split bigger problem with many degrees of freedom to smaller problems with fewer degrees of freedom. With or without tricks. Without tricks it doesn't work. And first trick is by Born-Oppenheimer to split electronic and nuclear degrees of freedom. In fact, we did everything last time with great help of volunteers from class who came up and derived and practiced calculus of taking second derivative of a product. But we are going to go over the same equations once again, discuss them, and this is a justified investment of time because it fits the development of class material, and many people who do not see it right now suffer from missing this knowledge at later stages when it is really needed to describe processes when the connection between electronic and nuclear degrees of freedom is not negligible. So for most of the course, and for some people for most of the whole life, any calculations are dealing with the almost independent nuclear and electronic degrees of freedom. Low temperature, stable molecules, just for characterization, no reactions, no light, no laser, no hot plate under the glass container. As chemists, you can give me a better word. Beaker? What else?
Round bottom.
Huh?
Round bottom.
Okay. Round bottom. But if you are not cooking anything, then you do not go beyond Born-Oppenheimer approximation. Right away, I was just scrolling back through my memory what I was telling here and checking if I did lie in anything. I didn't, but it may have appeared a little misconception, and we will come through it in details. The nuclear and electronic degrees of freedom are not completely decoupled. They are not totally independent degrees of freedom. The position of interatomic positions of ions, positions of ions, affect splitting of electronic levels, affect the orbitals. The reconfiguration of electrons in form of orbitals does affect internuclear forces, and this polarization of electronic clouds around nuclei make this Coulomb repulsion of ions weaker. This substantially changes potential energy surfaces. So we are not undermining this natural concept, this intuitive idea. The decoupling of electronic and nuclear degrees of freedom is happening in the following sense. Under Born-Oppenheimer approximation, there are no jumps between electronic states, even if we include time dependence. So each electronic state is an eigenstate that doesn't change. And there are no nuclear motion-induced superposition between different electronic states. So in this sense, absence of transitions. Of course, positions of nuclei affect energies. No transitions. So it is delicate, challenging thing, and later on, some of us may come back to it for practical reasons. But it's better to lay foundations right now. Okay, let's scroll through whatever we have. Yeah, we will do quantum mechanics. So in your homework, you may want to draw a picture like this, but for different number of ions or electrons, just as a practice. Do not spend more than 15 minutes. So 5 types of terms, and we split them onto whatever relates more to electronic and nuclear. I don't want to hide myself from camera. Okay. And formally, we are seeking solution in the form of product of overall wave function. Not here. It is more. Yes, here. We are seeking for the solution in the form of product of pure electronic orbitals that depend on the parametric positions of ions and nuclear wave functions which serve at the same time as expansion coefficients for electronic wave functions. So before Born-Oppenheimer approximation, it is this general form. After Born-Oppenheimer approximation, for a given electronic state, these coefficients chi are either 0 or 1. So different weights of electronic wave functions in the total wave function corresponds to superpositions induced by quantum properties of nuclei. And we are just going through the steps that allow to drop this connection. Instead of product form with several terms, tell that there is product form with only one term, electronic times nuclear. Good. We did plug this general term into the molecular Schrödinger equation and identified that there are terms where nuclear we did apply the property of orthogonality of electronic wave functions because they are good. And we did find out that by multiplying this all big molecular Schrödinger equation by conjugated electronic wave function with different index, I'm not showing it here, we found that there is a story about a snake and mouse, and we get rid of electronic wave functions and keep only the nuclear wave functions in all terms except the first one, where the kinetic energy of nuclei affect both electronic and nuclear wave function. I told this. Good. And then you guys helped to open this product and find out that there are 3 types of terms. The natural one, where kinetic energy is second derivative over position, right? If you do not recall it from kindergarten, you'll recall it from we repeating it here in the lecture. Second, over position, kinetic. So here it is kinetic energy of nuclei, so it's derivative in respect to positions of ions, applied to nuclear wave function, while electronic wave function is unchanged. So this term would correspond to standard, pure kinetic energy of nuclei. But other terms do have this derivative applied either to nuclear or electronic wave function, or only to electronic wave function. We have a strong and passionate desire to drop these terms, because we know that close to 0K, nuclei are not moving, and they for sure will be dropped. And we seek to give name to those terms that we are dropping, and after this, the wave Schrödinger equation for nuclear wave function will look in a standard way, without any mixtures and without any memory about electronic parts. And we will identify that it will be pure nuclear kinetic energy plus nuclear repulsion plus additional term due to polarization of electrons. So for nuclear part and for electronic, it is everything that has lowercase e applied to electronic wave function for eigenstate problem. Nothing new. We did this. I'm not going to tell anything more. I'm going to go over the things once again. I hope you will not object. But there are benefits, and I've learned about this stuff from this gentleman who was his author of this book, and he was in my thesis committee in the year 2000. So, derivative of two functions, first and second, 4 terms. We already did it. So, repeating, same thing. Second derivative of nuclear wave function. This is good term that we keep, and everything else is going to be erased. We just need to give it name and be comfortable and confident to address this term later. So, one of the questions in your homework is when non-adiabatic terms are not dropped. Plasma, reaction, fragmentation, explosion, high temperature, something like this. Extreme conditions with high temperature, high energy. Be creative. Well, for any process on stars or nuclear explosion, of course, forget about this approximation. But even at our bench lab, bench in the wet lab, some processes are away from this Born-Oppenheimer approximation. And one of the simplest and most peaceful examples when Born-Oppenheimer fails and one needs to take into account this terms, non-adiabatic coupling, is when you make your molecule or your nanostructure or your whatever impurity level in laser to emit light. How does it happen? You excited. So since you took physical chemistry, your instructor should have instructed you about Stokes shift effect, right? Please raise your hands if you haven't heard about Stokes shift. Okay. I don't. Very good. So it is nuclear reorganization, and it is typical effect that absorption and emission happen at slightly different offset, because ions reorganize upon photoexcitation. One thing. There is another aspect which looks very similar to Stokes, but it doesn't have this name. When you have several levels in your molecule, you excite higher up, and then it experiences cascade thermalization, relaxation to lower available. If you speak on the language of molecular orbitals, to like HOMO-LUMO transition or lowest excited state, and then it emits from there. So when it goes through this cascade thermalization, when it goes from excited to higher level to stay in quasi-stable state and the lower excitation, this transition includes non-Born-Oppenheimer dynamics. Thermal relaxation. So the relaxation from excited state to more excited state to less excited state occurs because ions are moving. And it is a very peaceful term. You don't need to blow up or ignite anything. It will happen naturally. So when you have your just creating low intensity excited states in any devices, any photoactive materials, it happens. Well, this was okay. When we did plug in general form of solution into molecular Schrödinger equation, we got several terms, and the first term was challenging, and the rest were simple. We already went through them. So here is the first term in molecular Schrödinger equation. Do you want to challenge me or complain that you do not like some of the notations or terms here? Well, I would like to use letter I for counting ions, but this is my understanding. Do you feel comfortable with this angular brackets here and there? So when we do have orthogonality, the property of this function b times function a, we are getting either 0 or 1. So this integration sometimes is replaced by b, a, or phi, b, phi, a notation. So you see it here, right? So this integration of these two functions. So angular brackets, some people like angular brackets more than single integration. That's it. So this is the part of molecular Schrödinger equation that we are going to draw. I have already excluded pure kinetic energy. So we do not have a term where the derivative of space is applied to chi, to nuclear wave function. We have only the term where it applies to electronic wave function and nuclear wave function, cross term, or when it applies only to electronic wave function. Well, here it is applied, the derivative over nuclear position to electronic wave function is applied only once, so it is non-adiabatic coupling of the first order, and here it is applied twice, so this one is second order. Even those brave people who ever consider non-adiabatic couplings in their works, they drop second order. So you will not see in most of practical works this term. Maybe if the application is very unpeaceful, if the temperature is extremely high. What else can we identify just looking at this equation? What is the only one equation that we need to remember from physical chemistry or quantum theory?
Momentum.
Yes. Can you? I don't want you to walk. You can just dictate me what to write.
It's negative I h bar squared, correct? Over.
No, maybe not.
No, just oh yeah, no, it's just h bar over 2m.
It is. You are speaking about kinetic energy.
Oh, kinetic
What
energy.
if it's just momentum?
Just momentum. It's derivative of r.
Yes, that's it. Right. So difference between derivative over r and momentum is just this constant. So I'm lazy to derive things. I'm going to skip some terms and just invite you to believe me. What if one day we need to find expectation values of some observables related to nuclear degrees of freedom? We will do contraction of conjugate wave function, like this, and chi sub b on another side. Right? This is something exotic. Let's focus on this term. So this is first derivative over nuclear degree of freedom applied to nuclear wave function. And here we have h bar and whatever. What if you take one h bar into here? Replace, remove the 2 h bar here. Put minus I here and maybe divide everything by minus I. You're following. Then this term can be called momentum operator over for ion number I. So this is investment into the far future. But now it's the best time to do it. So the practical part of the nonadiabatic coupling is the response of electronic wave function to shift of nuclei times momentum of nuclei. So if momentum is 0, if nothing is moving, this term is 0. It's very natural analysis. And if you go from quantum limit to classical limit for nuclei, then instead of, there will be no nuclear wave function. There will be classical variable of momentum, but it will stay here. So something exotic related to electronic part times momentum. So this term will survive even in the semi-classical limit when ions are classical point charges. Questions? Probably now we are passing most complicated point, and the whole course after this will be going down here. So theta stands for these terms when we do not have summation and do not have this nuclear wave function. So this theta AB is non-adiabatic coupling between electronic state A and electronic state B. So it's amplitude of probability of transition from state A to state B due to nuclear motion. Definition of non-adiabatic coupling. Only this term. This summation would not have B. Summation over A. This summation was present in all terms of molecular Schrödinger equation, but due to snake and mice, it disappeared, right? And we never had the B term, only A term. And here it dropped just the whole thing until the better times. non-adiabatic is some constants phi a d dr phi b times p. It's not. It misses some constants, but it is a thing that is possible to memorize, at least for me. So electronic transitions due to nuclear motion. Electronic transitions due to nuclear motion. Okay, and it is something you know. Non-adiabatic drop. All other terms have snake and mice and lose the summation. And it is the equation that you have already seen in the summary slide. So pure Schrödinger equation for nuclear wave function. Angela, can you just move this to across the diagonal? And the nuclear to nuclear repulsion plus polarization of electronic clouds is actual potential that one given nuclei is feeling. So, in some sense, it is surface potential energy, and the term is potential energy surface. 4 arrows. Maybe if I click to next slide, there are some arrows will appear. Okay, I agree. Right? So the non-adiabatic was dropped. This is kinetic. This is classical nuclear repulsion. This is electronic contribution to potential energy surface. And this is eigenvalue that one needs to find. Well, before we go to this picture. I know you may make a conclusion that things are boring, but this is theoretical background. As soon as we go to lab and practical, it will be more exciting. And in the theoretical background, it will become more funny and funny. It is very few steps separate us from more active and practical activities. So we still need to do this experiment in our thoughts, computation without computation, calculation without calculation, just analyze the shape of equation. Do we see any observations, any special features of this equation? Anything that may challenge our intuitive thinking? Anything that contradicts to classical mechanics? Let's look on the potential. Potential part, so Schrödinger equation has kinetic energy and potential. Potential energy has classical internuclear repulsion and contribution from electronic clouds formation. Good. Classical part, if you have ions charged with so much and so much, their coulombic repulsion will be always the same. But the contribution to internuclear potential, internuclear forces from electronic polarization does have index. Right? And this index comes from the electronic part. So there is still some connection between electronic and nuclear degrees of freedom. So for each position, we diagonalize electronic degrees of freedom, and the eigenenergy comes here. And whether it is ground state, B equals 0, or it is excited, B equals 1 or 2, contribution to the interatomic potential will be different. So electronic state presence of any electronic excitation in electronic subsystem does affect how nuclei interact. Right? So for ground and excited electronic states, the potential energy surfaces for nuclei will be different. Right? This is not an easy idea, at least for me. If you are so happy with it, I admire and applaud. So let's think about it once again. So how we can interpret just this simple equation. So it is very easy and natural to assume that we create, so since we have many ions, this potential energy and this R means that we have 100 of ions. So it is multi-dimensional profile. That's fine. We have a wild imagination. And it is easy to guess and assume and understand that if we excite electronic part of the system, this potential surface just lifts up by the amount of electronic excitation, right? No objection. But what this little thing prompts us, the shape of this potential energy surface will be corrupt upon excitation. If you excite further, it will be corrupt again. And the simplest form, well, corruption is not a good word. Modify. So, and the simplest modification, well, this simplest potential energy surface is parabola. And simplest modification is change of the equilibrium position. So, if you excite your electronic subsystem, the potential that nuclei experience will change equilibrium position. Ground electronic state. Phi A equals 0. And here we do have V and N plus E R E, or B equals 0. So we have equilibrium position or equilibrium. And we have some curvature of parabola. Okay. Now we are applying excitation. We are going to excited state phi sub A equals 1. So we not just shift this parabola up, we also shift it along the nuclear positions, so equilibrium point will be different. So this will be V sub n plus E, as incorporate the plus E sub B equals 1. So this term that changes, it is how eigenstate of electronic system depends parametrically on positions of ions. And this is a complicated function. So the drawing here, position of equilibrium position of ground, equilibrium position of excited. This is very oversimplified picture. In fact, it is multidimensional surface. It is not only shift in equilibrium position, it changes curvature. And parabolic shapes is too simple. In fact, they can be, especially if you have chemistry with activation barriers, it can be something very wild. But the simplest thing that we can imagine and immediately analyze to maybe conservative, non-violent systems, when nothing reacts, just excite, slightly shift, change color of emission and absorption. This is a good picture to imagine. So if you were in physical chemistry, you may have seen similar pictures, but we were not telling about fundamental aspects why it happens. now we have a little bit more idea about this connection between electronic and nuclear degrees of freedom and why this shift occurs. Well, if you go to next excited state, it may shift further in the same direction or different and experience different shapes. Or it can become something violent. For example, it can become dissipated, so that system will go away, molecule will evaporate. We don't care about specific form of the excited state potential energy surface right now. We're just telling that potentials and forces that nuclei are experiencing do depend on electronic configuration, on electronic state. Okay? Yes?
So how similar is this to like Marcus theory? Like, is this like just looking at like one area in general, but like Marcus theory is looking at the interaction between the two? Because I remember two parabolas is part of Marcus theory.
This idea can serve as a fundamental basement for Marcus theory.
Okay.
And in practical aspect, if you explore something, these calculations based on this idea can serve as an input that allows to parameterize Marcus theory.
Okay.
So Marcus theory is great, but in some sense it is phenomenological. It doesn't tell where we take shapes of these parabolas. It's just we take them and then compute the transfer rate.
Okay.
Okay, make sense?
Mm-hmm.
And when I was doing this picture a couple of years ago, I was more wild and did this shape, but idea is the same. Potentials and interatomic forces that ions are experiencing depend on electronic state. Not bad. I told you at the beginning. So you cannot catch me. I never told that electronic and nuclear degrees of freedom are completely decoupled. They have connection through this E sub B of R term, right? Through their contribution to potential energy surface. Born-Oppenheimer approximation tells that we do not have jumps between the states. And when life is boring, we include time dependence. Like going to animated pictures, movies. Same in science. When we are bored with time independent Schrödinger equation, we are going to time dependent. It's natural idea. So how it answers how we function, how these shapes of orbitals change in time. And we do have an intention. Right now, we are not going to redesign the bicycle and come here and develop new theory. We just overview what does exist by today. And from practical reason, I know what I'm going to tell. From practical reason, we are not going to undermine all computer codes for computational chemistry that do exist. And they, fortunately or unfortunately, they do neglect quantum properties of nuclei. In all computational chemistry software, nuclei are assumed to be point charges. So although you guys here, including myself, are so smart that we know how nonadiabatic couplings works and how these jumps between electronic and nuclear degrees of freedom are arranged, because nuclear wave function does exist. In all pieces of quantum chemistry software, it's just point charges. What is our goal? For today, I will just declare a goal and briefly go through things, and when we meet next time, I'll go into details. So we want to see the transition. Right now we do have two parts: electronic Schrödinger equation and nuclear Schrödinger equation that were derived from general molecular Schrödinger equation, right? Now we are going to take nuclear Schrödinger equation and simplify it towards Newton's equations in a careful way. In fact, I'm going to scroll anywhere. It will be Newton's equations with this potential. Right? Newton's equation of motion for point charges, where the potentials do depend on electronic state. That's it. But we are going to slowly do it and discuss what we see on this rule. No questions? So how do we do it? Well, if we do know time independent Schrödinger equation, we can convert it into time dependent. Right? So you just take this, whatever serves the role of Hamiltonian, d dt. We add dependence on time for our wave function. Whatever was as a Hamiltonian here, x and chi of and t. Right? So this is the equation that governs change of nuclear wave function in time. I'm aware that some of you are doing research related to nuclear wave functions expanding in time. And if you are doing so, I assure you that you are unique, and majority of either computational chemists or physical chemists or theoretical chemists do not touch this area, trying to run away. So if you're exploring nuclear wave function, you are brave. So suppose we know how the nuclear wave function evolves in time, and we ask the same question again and again. A theorist and computational chemist is a humble servant of an experiment who needs to predict outcome of an observation. Observable. So all these wave functions, all Hamiltonians are abstractions. We need something that can be measured. Right? And the simplest thing that can be potentially measured, we are not going to exotic things, are position and momentum. And if one formulates the expectation value of position of each ion based on solution of this equation, one will arrive to Newton equation of motion with this potential. It is a summary of our next video on whatever, Thursday. So how do we call it in fundamental quantum theory, this transition? Especially if you have some flavor of physics background.
Kern-Fest theorem.
Yes, yes. So transition from quantum to back to classical Kern-Fest theorem. Nothing new. You already discussed. Well, we are leaving this Ehrenfest theory and transition to point charges to next meeting. But what can we do intuitively before we go into details? When this transition makes sense? When complicated wave function can be approximately characterized by position of ions, one or several. if the wave function is delocalized over whole space highly oscillating, where is the, so it is R, one-dimensional, this wave function, high, where is the position of the point charge? Does the concept of point charge make sense for such crazy wave function? No, too delocalized. But what if wave function is, it may oscillate, but it is consolidated in the very narrow region around some position. If right now we are thinking as pure mathematicians without connection to practice, if by some reason we find all the time that the wave function is localized in the narrow vicinity of some point in space, and the width is really negligible, then to some extent we can just track the average position of center and forget about shapes and these fringes. So it will make sense. So we have probability of like proton to stay a little further away, a little closer, but in average we know like hydrogen to hydrogen distance in molecular hydrogen, right? And this is not very bad idea, especially for practical reasons, because any quantized degrees of freedom makes hard complications. If you can neglect or temporarily forget about quantum properties of some degrees of freedom, it will make problem like many orders of magnitude easier. Its drop in precision is justified by substantial, very substantial drop in numerical cost. So, what is the keyword?
Delta distribution?
Yeah, it's limit. Now I'm going to synthesize what London suggested and what I was thinking myself. So if nuclear wave function is localized, then point charges or classical path point charges are good. And London told that instead of this clause, he told if limit of nuclear wave function of R goes to delta function of R goes to delta function of R minus average position of R, then concept of point charges is justified. Right? I just translated your words. So if you have more complicated thing, it will not work. But if you have wave function localized around one center, good. And luckily or unluckily, for most of molecules, it is the case. So violation from localized Gaussian shape occurs during reactions, during femtosecond femtochemistry experiment, when you excite something with few femtosecond short pulse and something launches, or when temperature is elevated, when Born-Oppenheimer approximations is broken anyway. But if we are conservative, peaceful, non-violent, non-reactive ground state things, point charges are very good. Good. Center of distribution, molecular Schrödinger equation, and time-dependent Schrödinger equation for nuclear part. So when right now I'm about to stop. So where we stop today is for electronic part. We have time independent Schrödinger equation. For nuclear part, we have time-dependent Schrödinger equation, where this eigenenergy tunnels through and redefines interatomic forces at each distance, depending on electronic state. What are our intentions? To convert this equation into something much simpler, into Newton equation of motion. Okay? Should we? Okay. You saw this. So this part can be defined as potential energy surface. Draw example. No, not good. So again, I started thinking and going through this aspect 10 years after getting the degree. So you are away of typical degree holder 10 years above. And I was doing, when I was not independent but subordinate, like apprentice of another PI, I was doing practical aspects, like do results, give to the boss, and who cares why they need it. And once I expressed curiosity and asked, like, we are practically looking for change of electronic function when nuclei are changing, but what is the term of Hamiltonian responsible? And I was expecting that answer will be like electron to nuclear attraction, and I was so surprised that if you derive this equations, the non-adiabatic coupling appears from quantum properties of nuclear kinetic energy. Nuclear kinetic energy, quantum properties, if there are, it is where these transitions are coming. And right now, you got a chance to develop this fundamental if you ever need to go to this exotic but very rewarded area of research in computational chemistry. Starting from next lectures, we will roll down to simple, traditional, easy to get theories and approaches. Done. And then classical limit, potential energy surface, optimization of geometry. Plan for next end of lecture. And I have many slides about our practical activity in the lab, but I think they need to be shown in the lab. Thank you for coming, investing your time, not making noise when I'm speaking. And I look forward to see you Wednesday evening in the lab, if you are on the part of this course, and on some additional meetings if you are doing research. Meeting is done. Thanks for coming. I'll stay here to answer any questions.